Welcome to BKW Physics. I'm Mr. McConley. Today we're doing radioactive decay, and another word for that is transmutation, because as you break down the nucleus, it transmutes into other elements, so transmutation. And some of the radioactive emissions we've already spoken of in Rutherford's experiment were alpha, beta, and gamma. And we showed how his experiment was a breakthrough in thinking because of the way he determined how to find those using the left-hand rule. And today we're just going to talk a little bit more about these emissions, and I'm going to give you an example of how you might see some of them. So let's start with alpha. Alpha, which is a 4-2 helium, has a speed of between 10,000 and 20,000 miles per second, but you can stop it with a piece of paper. An example of an alpha radioactive emission might go something like this. If you had 226 over 88, which is Ra, and you just let it sit there, it would start naturally decaying, and it would give you, as an emission, a helium, which is alpha. There's your radioactive emission. Plus it would give you 222 over 86, which is Rn. Now for physics purposes, whether you know your elements does not matter in physics. The physics concepts I'm trying to show you are the concepts of what is emitted and the general principle that you need to balance the equation. And everybody should know that from chemistry, so you add up the top, and it should equal the top over here. You add up the bottom, and it should equal the bottom over here. Okay, so that's the basic concepts that you need to know, not anything about the elements or other. Okay, moving on to beta. Beta travels even faster at 100,000 miles per second, and you need an inch or two of solid material to stop it. And you also get this thing called an antineutrino whenever you have beta decay. So let me give you an example of that. If you were to have 234 over 90, which is TH, and you let it sit there, it would naturally start to decay, and it would emit a beta particle, which is a 0, -1. There's your beta particle right there. It would give you the element 234 over 91, which is PA. I don't know my elements very well, so I'm just copying it off a piece of paper. But it would also give you the antineutrino, and the interesting thing about that is we don't really, as scientists, we don't have a great understanding of the why and what the purpose is, the mechanism, the purpose there. But we know it always happens. And this is a little bit tricky here, you notice when you go to balance, because you have a -1 and a 91. So this element actually has a 91 in the bottom, where your original element only had a 90. Okay, so just remember when you have negatives, how the balancing works. You can also get gamma. And gamma is like high energy X-rays. So when you go to the dentist, you get an X-ray. That's an X-ray. But if you ramp the energy up, and remember from your reference table, you can see the progression of the different waves. If you ramp it up to gamma, that's what we're talking about now, and that takes a foot of lead to stop. Okay? Next, positron. Positive electron. So it's a 0 positive one. And I put the little quotations here because it has the same speed as the beta did. It can be stopped by 1 to 2 inches of solid material. But up here in beta we got an antineutrino, then if you follow the pattern, we're going to get a neutrino when we do positron decay. So I had an example of that also, which is if you took 30 over 15 P, and you let it sit there, it would start naturally decaying into 30 over 14, which is Si, plus your positron, plus this neutrino. So everything I've showed you here is a natural decay. meaning you didn't need to do anything to get it started. But over on this side, I want to show you just an example or two of what an induced radioactive decay would look like. So induced means you have to do something to get it started. So if we took, for instance, because we have alpha here, what if we do induced alpha? What might that look like? Well, an example would be if you had aluminum, so let's say 27 over 13 Al. By itself, it's pretty stable. But if you hit it with alpha, that's the inducing part. So whenever you induce something, it happens on the left-hand side of the arrow. So if you hit it with the alpha, right there, now it will start to change or transmute, and it will turn into 30 over 15p plus a neutron. And you can check and see that that balances out there. One more example, just for completeness sake. If we, let's do this one right here. Let's go to beta, and let's do an induced beta. So if we took 14 over 6, C, no, that's not going to work. I gotta use a bigger element. Let's use this one. 100 over 46, which is PD, and you hit it with a beta, what's going to happen here? Well, what's going to happen is it's going to start breaking down, transmuting. It's going to break down to 100 over 45, which is RH. So you can see that on this side, these happened naturally. There was nothing that you needed to do to the original element, and it would start breaking down. As with these, you had to hit it with the element, so this one is called induced alpha, and this one's called induced beta, because you need to hit it with that radioactive element to get things, or radioactive emission, to get that thing, to get that chain reaction started. So for today, that's transmutation physics.